So we're going to draw the Lewis structure. So for both of these, the first thing we're going to look at is we've got 3 and then 7 times 3. So we have 24 valence electrons to deal with. I'm going to put the aluminum in the middle because it's odd man out. I'll put an aluminum here, and then I'll hook all these chlorines up to it. And so that uses 6 of my 24, leaving me with 18. And since these halogens can only make one bond, and they need to see 8, that's what the Lewis structure is going to look like, even though the aluminum is missing 2 electrons because it's supposed to be missing 2 electrons. That and boron are violations of the octet rule, meaning they only want to see 6 and not 8. So there's my Lewis structure for this. Actually, I could probably just do this. Make it easier on myself. And put the chlorine right there. And now it's also the 3D structure. And I'm saying 3D with quotes because it's a 2-dimensional structure, right? It's trigonal planar. So is there a VSEPR structure for this one? No, there's no lone pairs on the middle atom, so no. But the molecular structure is going to be trigonal planar. All right. So the next one, I've got 4 plus 3 times 1. Whatever, plus 6 plus 1, 14. 14 electrons. And so I'm going to have a carbon with some hydrogens on it. And then we're going to have an oxygen and a hydrogen attached to that. And I still have 4 more electrons to deal with, which is good because my oxygen needs to see 2 pairs. All right, so how many central atoms are there? 2. All right, so I've got carbon and a hydrogen and a hydrogen, and we'll do this. Hydrogen. Actually, I'll put this one back. And then I got an oxygen, and then I've got a hydrogen, and then I've got a lone pair going this way, and a lone pair going backwards. So this is the 3-dimensional structure for my VSEPR. Okay? Are we all right with that? What are the structures around?
The carbon, oxygen, and hydrogen are bent.
Not for the VSEPR.
It's just
Both of them. Both that one and that one are tetrahedrals for VSEPR. Well, this one doesn't have a VSEPR structure. Let's just do that. There's a VSEPR tetrahedral right there. And then for the molecular, there's a tetrahedral. And there's a, what'd you say, Diego? Bent. So this tetrahedral is around that carbon, and this bent is around that oxygen, because if I get rid of these electrons right here, all I see is a bent structure. I must have asked, do they mix with water? Trick question. Half of it's a trick question. That's ionic. So yeah, it's going to mix with water because although there isn't an aluminum solubility rule, there's a halogen or a chloride solubility rule, and it says they're soluble. So aluminum chloride definitely dissolves in water. Last term stuff to remember this term. And then Diego asked me early on in this class, so over here, this over here is polar. Are we okay with that? Sorry, everybody okay with that? This being polar? Yeah. We get these electrons here traveling towards the oxygen down here. And this side over here is nonpolar. It's small enough to be soluble. What do I mean by that, Diego? Small enough.
That it's more polar than non-polar.
And what would I mean if it was larger? And
Add more carbons to it.
yeah, so
Non-polar.
we go CH. This is just a CH3OH. So what if it was a CH3, CH2, CH, CH2, CH2, CH2OH? What if we did that?
Make it non-polar.
Yeah, so all of this hates water. And only this little part over here likes water. So the cool thing that this would do is if you were to put this in water, it would stand up on its end with the OH in the water and the rest of it sticking out, trying to get away from the water.
Wait, so with the aluminum chloride, I don't understand why it mixes with water.
It's an ionic substance.
Okay.
There's no polar non-polarness to this. This isn't a covalent compound. That's why it was a trick question. Are you worried that this should be completely non-polar because everything's in equal and opposite directions?
I thought the chlorides were soluble. I thought that only polar things could mix with water.
Okay. If we're talking about covalent compounds, then only polar things can mix with water. But this isn't a covalent compound. This is ionic.
Right. I don't understand.
Does table salt dissolve in water?
Yes.
Okay. What kind of compound is table salt?
What's ionic?
That's it. That's the end of it. That's why I said it was a trick question. Emily, what's wrong?
I don't know how to put it.
Why is it bugging you? You have a whole list of things memorized in your head that'll mix with water, right?
Right, and
So-
that makes sense to me, but then this sentence says that only polar things could mix with polar things.
Only polar things. When we're talking about that, I'm talking about covalent compounds.
Okay, that just refers to covalent compounds.
Because can you have polar ionic stuff?
No,
Why not?
because it doesn't share.
Doesn't share electrons. Yep. Feel better? Mildly. Not 100% better.
It's still frustrating, but I get it.
Okay. All right, so we're going to do the formal charges on the methanol. So let's do, I don't know, whatever. We'll do the carbon first. So I've got, how many valence electrons for a carbon? I got 4. Number of lone pairs of electrons on that. The answer is 0. Number of bonding electrons, 8. Divided by 2 is 0. Everybody okay with that? Each of those bonds is 2 electrons. So there's 4 bonds, so that's 8 electrons. Half of that, 4, then we get 0. Good? Yep, okay.
I mean, can't we just be like 1, 2, 3, 4? There we go, 4.
4 what?
4 lines.
But what's the...
Symbolizing bonds, like obviously there's 2 there, but you only want 1, 2, 3, 4.
I don't understand how that's going to help you figure out what the formal charge is, just counting up the bonds.
I just think of it as carbon wants to be connected to 4 things, and now it's connected to 1, 2, 3, 4 things. Like if they share 2 electrons, I know that, but that's just
Okay. As long as you can do it in a way you can remember how to do it, that's fine. The oxygen has 6 valence electrons. It has 4 electrons that are non-bonding pairs of electrons, and it has 4 electrons that are bonding electrons. I have that, and I end up with a 0 again. The hydrogens each have 1 valence electrons, no unbonded. They've got 2 electrons in a bond, divided by 1, 0. So the fact that the formal charge for each of these atoms is 0 means this is a really good-looking Lewis structure. All right, what is the specific heat piece of metal? So I'm going to take this and go 4500 calories. Then I'm going to do, what do I want to do first? We can just, how about we subtract off this 68 Fahrenheit? So 660 78? No, 72? 82? 82. Yeah, 18, 82. Yeah, all right. So then I'm going to subtract 32 from that, then multiply by 5/9. Making sure that's in parentheses. So I got 682 minus 32 equals times 5 divided by 9. And I get 361 degrees Celsius. And so I'm looking for a specific heat. So that's calories, 4500 calories per gram. 1250 degrees C, 361 degrees C. So 4,500 divided by 361 divided by 1250. I get 0.01 calories per gram, 0.010 degrees C. 2 sig figs. Does that look good?
I messed up somehow. Converted it to Celsius first and then subtracted. I got like 379.
I'm thinking it's just a error in your math.
I got 20 degrees Celsius and 399.
I think it's probably because you didn't carry enough decimal places during the conversion. So when I know there's only 2 sig figs in this, but when you're actually doing the math, you carry all the significant figures until you're at the very end, and then your answer is the only thing that the sig figs apply to. So if you sig figged in the middle there, then you probably had enough error to throw yourself off
By that much?
by that much. It feels like a lot, but is there a huge difference between 361 and 379 degrees Celsius? It's 18 degrees, but it's 300 and something. It's a small portion of the total temperature. So the further away your initial mistake is, the more it gets magnified when the numbers get larger.
Do you want us to switch to this calories? I kept my answer in kilocalories.
It's usually not listed in kilocalories. It's not an invalid unit. It's just your what's your number look like? 0.00001? What?
It was 0.005.
Not with kilocalories. Here, you should have 3 more zeros in it. Okay. So there's some math issues there. Okay. The last one, which items are able to violate? In which way do they do it? And is this violation certain or just a probability? So we talked about it earlier. We've got boron and we've got aluminum. And these things only want to see 6 valence electrons, and this is a must. This has to happen. Okay? And then we've got sulfur and phosphorus, and they could go more than 8 electrons. And it's a maybe. It'll do it if it has to, but it doesn't need to do it. All right.